Mesdames, Messieurs, bonjour, bienvenue à Lausanne. So, I'm going to talk about, the title about from location privacy to genome privacy. This is work done with a number of people. Here are the computer scientists, and here are the geneticists and the clinicians. So, before going to those, let's say, specifically to those aspects, I would like to introduce, let's say, the big picture. Many of us on this room, I think, have leveraged their career by taking advantage of the convergence that has taken place between the world of telecom and the world of computing that has led to modern IT, and this is probably best incarnated by the smartphone, which is both, a telecom and a computing device. The next big thing is, in my opinion, going to be around the emergence of digital medicine, and which encompasses many aspects, but in particular genome sequencing, for reasons I'm going to explain in a minute. And this is explained in many books, but I can recommend one, in particular, The Creative Destruction of Medicine by Eric Topol. The convergence of those two things is going to lead to something I like to call the last inch, by reference to the last mile that is well known in telecom. The last inch is when devices get very close to our body, and the last inch can even be negative in the sense that the devices are within our body in some cases. So this world tends to work in base 2, this world more in base 4, but this is just a matter of a small difference after all. Okay, so privacy, how it all started. If you look at the history of privacy, the first texts that appear were motivated by the emergence of the camera at the end of the 19th century. And this led these two gentlemen to write a seminal paper called The Right to Privacy, and the concern was the photography without consent. So the emergence of this new tool led to the emergence of the very notion of privacy being a problem and becoming a problem for society and having legal regulations. This was more than 1 century ago. In the meantime, modern observation tools have emerged. The cellular phones that we like to carry in our pockets, the trackers we have with us. Second one that has been already discussed by the previous speaker, the online social networks. And more recently, the genome sequencing, on which I'm going to devote a bit more time. Okay? This is just examples, there are many more, of course, but the very existence and availability of these tools generate a certain number of problems. Okay, so I'll start with location privacy. Location privacy is related to the fact that we like, as human beings, to make use of these mobile services. We go around, we activate them, and by doing so, we activate service providers, so-called location-based services, that are able to provide service based on our location. Okay. By doing so, we leave a digital trace around that we are in practice unable to erase or to scrub. Right? So work we've done in this area consists in trying to quantify, so by how much are we harming our own privacy when we make use of those services. There have been a number of privacy-preserving mechanisms proposed, but so far there was no uniform framework to do so. And so as long as we cannot put numbers on solutions, we are in an awkward situation because we are unable to compare them. So we need those numbers. Right? So how do we compare different mechanisms and which metric do we use? So for this, we have taken the following approach, and this is, I have to apologize, this is the busiest slide of this presentation. Let me go through it step by step. So we're going to start from here. So each of these rows here is a user, so each of us, right? And each of us actually is activating this service. And we assume here the activation is to be synchronous, but it doesn't have to be the case, just to simplify the model. So here we activate the system. We're saying, okay, we are in a room Richemont of Lausanne Palace, and a bit later we are going to be elsewhere, and so on. Tac, 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 tac. In the future, now, actually, nowadays, this information goes directly to the location-based service that can make use of it. In the future, the hope is that this is going to become a bit more sophisticated, and those data are going to be made less precise on purpose, on our phones, on our smartphones, in order to leak less information. And so for that purpose, the location is going to be blurred in some ways, become less precise, and the identifiers can be even swapped. Okay? So let's call these the observed traces, or traces that are observed by the location-based service. One dimension that should never be forgotten in such systems is that the location-based service, which we consider here to be the attacker, actually has also background information. He knows the daily commute of people. He can check online social networks. He can have a lot of ways to corroborate data. And so we'll assume that this background information he can let's say, incorporate or model by something that is, a tool that is well known that is called a Markov chains, which is essentially a probabilistic mechanism by which you can associate the probability for one person to move from one place to another based on the context of that person. So based on the background information and on the observed traces, the attacker is going to perpetrate a reconstruction attack, so try to know as precisely as possible where a given person was at a given instant. For example, who was with whom, and how many people have gathered, and so on. Okay? So from this, we can assess the correctness of the guess of the attacker. And this is going to be the only analytic expression that I'm going to inflict you, this is going to be expressed as the sum of the product between the probability of making a given estimate based on some observation multiplied by the magnitude of the mistake that is made at each time. And for example, in Euclidean space, this can be just a distance between the estimate of a given location and the truth, and the real location. Right? So a location privacy preserving mechanism will do essentially two things. One, it will drop the least significant bits of the coordinates on the x-y axis, assuming a 2D movement. Okay? Number one. And number two, it will hide some of the locations. It will just say, okay, this request I'm just not going to show, for example, in 10 or 20% of the cases. Okay? So we'll call an LPPM, so location privacy protection mechanism, with those three parameters, mu x, mu I, and lambda h. Okay? So here is just an example, just to show how this can look like about mobility in a given region with a certain number of users by making use of those two protection mechanisms. And the way it would look on a plot is the following. Here on the left-hand side, you have on the x-axis, the hiding level, so the proportion of a request that has been dropped, right, from 0 to 1. And here is the incorrectness of the localization of the user. So unsurprisingly, and this is done with an LPPM 00 star, so star is the x-axis, and 00 is the number of bits that have been dropped. So each time the location is provided, the location is precisely the one that is provided. In that case, as you can see, the incorrectness is growing, unsurprisingly, when the proportion of dropped locations is increasing. Here is a similar scenario, however, in which the number of dropped bits is 1 and 3 on the x and y axis, respectively. In that case, we have a similar allure, unsurprisingly, but it is a bit higher because there is this blurring of the location. Now, the important message here is that the amount of mistake made by the attacker, right, this incorrectness, is actually can be used as the measure of the privacy. So it's a very simple definition, very intuitive, and that for some reason had not been proposed before. It's just that it is by how much the attacker is wrong that we measure the level of our own privacy. Okay, so let me conclude on location privacy. So as we see, it is a major challenge, and the quantification is expressed as the adversary's expected estimation error, so the incorrectness. We have seen the techniques to protect privacy, location privacy as such, and we hope that those to be implemented in the products in the future. And one aspect that I haven't addressed, but I mentioned this just as a bullet, and there's been a number of contributions by us and by other people on this topic, which is that as soon as we reduce the privacy, the precision of the location in order to protect privacy, we are at risk of hampering the quality of service, because the location is going to be less precise. Okay? So there is this trade-off between privacy and quality of service that has also to be taken into account. So you find more information at this website if you have an interest on this. All right, now let me move to the second part, which is genome privacy, which may sound to be, say, how can you connect location and genome, right? Well, we're going to see that actually it makes sense, at least I think. Okay, so first of all, let me say a few things about genomics. So first of all, the genomic avalanche is coming. It has been announced for a while, but now it is really getting real in the sense that the cost per sequencing of a human genome is reaching, is 1,000 francs or even below, which means that it is the price is equivalent to a usual medical examination. Right? It used to be impossible, then it was for a while super costly, but now it's becoming available. So the social consequences of this has been anticipated by a number of authors and by also a movie, Gattaca. How many of you have seen this movie? Please raise your hand proudly. Okay. Huh? It was crap? So, well, we can discuss it if you wish. Yet, I think it would be a valuable homework for those of you who have not watched it, to watch it nevertheless. Now, not everything in that movie is correct, right? But for science fiction movie, it is exceptionally good. Right? Let me put it like this. Now, one mistake that is in the movie is that they present genomics as being deterministic, which actually is wrong. Right? But apart from that, it is, let's say, thought-provoking as such. Okay, now let's look at modern medical use of genetics. So genetics is used for multiple reasons, and the reason, there are one important aspect is that it can help early diagnosis of serious diseases. Number one. Number two, it can help to fine-tune treatment to the genetic profile of people. And this is, medical doctors believe that there is a tremendous potential in that area, in the sense that, as we know, medicaments are good for some people. A given medicament can be good for a person, but bad for another one. Likewise, the dosage varies tremendously from one person to another. Okay. So 23andMe is an example that was mentioned previously by Bala. It's a company that offers you the opportunity to have your own genome sequence without asking any medical doctor. You just send a sample of saliva to the US, and 2 weeks after, they open you a web account where you can read about your genome and about your medical profile and so on, and learn about all the diseases that might affect you. Okay, so this has been popularized by the case of Angelina Jolie, who decided some months ago, as you know, based on her genomic profile, to have a double mastectomy. Okay, so let me just mention very briefly the SNP, right? This is one. Okay, genomics 101 in a single slide. Okay, I just need to introduce one thing, assuming that you might have maybe a bit forgotten your biology course of high school, right? So the thing is that each of us, we seem to be analog, but we are digital. Right? We are digital in the sense that there is the digital sequence that is present in each and every of our cells, right? Which may seem to be impossible, but this is how it is. It's a fact. Okay. Now, most of us have a genome. All of us have a genome that is very similar to each other, which is the reason we look alike. to some extent the same way, right? But however, there are some differences, and the let's say most relevant of this difference is captured by the so-called SNP, the single nucleotide polymorphism. So these are the positions in the genome where there is a difference with respect to the reference genome. Okay, SNP, the SNP. Okay, now the next slide is about, I have to be a bit explicit here, but I guess everyone here is about 18. The next slide is about sex. Okay, so how to make babies? It's a user's guide, just in case you wouldn't know. So to make babies, you need essentially two people, a father and a mother. Okay, well, you know, some things evolve, but this is tend to be very relatively stable, right? So each of them is going to produce gametes, right? So each of us, we do have this double string of identifiers, and the SNPs are here somewhere, right? So the variations. So the gamete production on each of the sides is done by all of us who are still fertile. Okay, so here is going to be on the side of the father going to be spermatozoid, and here ovula. I told you I would be explicit, right? So the gamete production. So most of us are currently doing this in this room. We produce those, right, without noticing too much, I guess. So the gamete production will be, there is going to be a selection across those letters, if you wish, and this will lead to gametes. Okay, here's one gamete, bam, it's going to be used afterwards. Okay, same thing on the ladies' front. Okay, the random selection of those. Now the combination of the two happens either. Now I got your attention, right? Happens either in utero or in vitro. Okay? I guess the first, I know actually, the first version is probably the most enjoyable one. Okay? But still, voilà. So, and the combination of those two leads to a child. Okay? Good. This is how it works. And actually, all of us went through this, right? The first thing we did, right? Remember? Okay, good. Now, what is the threat? The threat is leakage of genomic data. So, revelation of privacy-sensitive data about about a given patient or person, right? Predisposition to disease, ethnicity, paternity, or filiation. So, as a consequence, denial of access to health insurance, mortgage, education, employment, blah, 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 blackmailing, stalking, and also cross-layer attacks. So, trying to make use of those data and combining them with other sources. Okay. So now, this being a relatively new field, there are a number of misconceptions in genome privacy, and I'm going to mention only one. But there are 7 of those, which you can find on my homepage if you wish, and we can discuss over lunch if you're interested. So don't be surprised there is a number, but it's going to be the only one I show you. The misconception is that genome privacy is hopeless because all of us leave biological cells, hair, skin, droplets of saliva, wherever we go, which is true, right? Those cells can be collected and used for DNA sequencing, right? So it seems to be a lost cause, right? Trying to protect genome privacy is a lost battle. What is wrong with this reasoning? Actually, I'm asking a question so that I can drink a bit of water. So what is wrong? Yes, absolutely, very good. I'm impressed, actually. So collecting human biological samples and sequencing them is expensive, illegal, prone to mistakes, and non-scalable. Well, cannot be done en masse, right? Even if sequencing techniques keep improving. Right? Absolutely. Thank you. Great. Now, so we have worked on this topic for the last 2 years, and I've learned how to deal with medical doctors, which, well, is interesting. Okay. So I'm just going to touch one aspect, which is the quantification of kin genomic privacy, and leave everything else is. I mean, everything here is online. So if you care for this topic, so quantification of kin genomic privacy. So let me explain what this means. let's go, so if we go to Facebook and consider the profile of this person, which we had to anonymize, of course. So let's call this person, let's say, Urs, for example, right? So here's Urs, and here is a Facebook profile. And Urs has a family, and he puts here his family members. Okay? Here they are. Okay. Now, Urs also has an interest in genetics and went to 23andMe and then got his profile and then has uploaded his profile on OpenSNP. OpenSNP.org is a profile. Remember what a SNP is? So OpenSNP.org is a website where people can upload voluntarily their own genome. So why people do so? Well, it's mostly Americans, actually. And, you know, now, Americans are human beings, right? We know that, but they tend to be slightly different from us culturally. So they behave different in ways that are somewhat surprising. Yet those things are actually coming here as well. And I know even Swiss people who have done this. Okay, now an attacker can correlate the two things. I can say, here is the genomic profile of Urs, and here and know who the relatives are, right? So, well, as we have seen how to make babies, there is correlation between the genomic profile of relatives, of course, right? So remember how we quantify location privacy. Now, how do we quantify genomic privacy? So, how do we help a family? So assume that in a family, someone is absolutely willing to upload his or her genome online, right? Maybe one of your cousins wants to do so. Then you have to talk about it, right? And say, okay, here is the actual genomic sequences of the different members of the family. So let's apply something that we call a GPPM, Genomic Privacy Protection Mechanism, and decide which subset we are going to allow to upload in such a way that a minimal harm in terms of privacy, genomic privacy, is going to be made to the family, right? So now, to do this, we have to take also into account the background of the adversary, right? And the background of the adversary is the fact that he easily can know how the family is constructed, okay? He can know also the correlation between SNPs, okay, because SNPs are not mutually, let's say, statistically independent from each other. He can also know the a priori values of each of the SNPs, okay? And based on this information, he will perpetrate a reconstruction attack, right, by inference. And then from that, it is possible to quantify the genomic privacy of that given family, and then the health privacy, because from the SNPs, one can compute the predispositions to specific diseases, including Crohn's disease mentioned previously, or Alzheimer's, or many, you know, after all, we know how it is, right? And so based on this, one can refine the GPPM and fine-tune it. Ça va? Verstehen Sie mein Deutsch? Okay. Good. So from that, it is possible to compute. So here we take one specific concrete example from a family. Now this family, these are Mormons, right? And Mormons like to have many kids. They know how to make babies. So here in this specific case, there's a family with 11 kids, right? Rarely seen today in Switzerland. And here are the two parents, and here are the 4 grandparents. So the question is, what happens to this guy, assuming that little by little we reveal the genomes of the others, right? And so here you can see, so I'm going to skip the details for the sake of time, but here on the x-axis you have the revealed genomic profiles relative after relative, and here the privacy level of this person. Unsurprisingly, the more you reveal, the less, the smaller becomes the genomic privacy level of this person, right? This is based on 80,000 SNPs of the first chromosome in this specific case. This can be extended to a global privacy of a given family, and is shown on this slide. So again, here in this specific case, the x-axis is the percentage of SNPs that are revealed, and the y-axis being the global privacy level. Now you see here 3 colors because there are different ways to compute this privacy, but the allure is pretty much the same. Okay, let me conclude on genome privacy. So the genomic avalanche is coming. Just a very specific example. If you, the CHUV, so the Lausanne University Hospital, nowadays, if, for example, you break a leg by getting out of Richemont room today, you get to CHUV, everyone there is offered the possibility to donate a sample of blood and to sign a consent form. Okay, and the consent form is to accept to be sequenced. So and this is actually going since January, and the plan is to collect 15,000, let's say, blood samples per year over 2 or 3 years, and to sequence all that stuff. It could tremendously improve healthcare, notably through pharmacogenomics, although the profile, I mean, this is not yet completely demonstrated. But this will work only if citizens can trust the whole process, right? And so the tool that we know, the cryptography, security protocols, database, differential privacy, anonymization techniques, blah, 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 that are already used for privacy protection, notably location privacy, can and should be used here, but of course need to be properly adapted. Okay, and you find more stuff here. If you're intrigued by the topic, we have a survey, a very gentle survey on 6 pages that describes the whole thing. That is also available online. Okay, so this to conclude on the notion of holistic privacy. So the more observation tools appear, such as genomic sequencing and online social networks and mobility, etc., we have to think holistically about this whole thing to try to understand what privacy is going to mean in the future. Okay, let me now come to an overall conclusion. So the assault on privacy is a huge research challenge. We have seen location privacy, quantification at the physical level, so in terms of XY coordinates, and there is ongoing work at the semantic level in different research groups in the world. We have seen that the online social networks are part of the background knowledge of the adversary and should always be taken into account. And general privacy is still in its infancy, soon to be very hot, and the first results are coming out. Thank you for your attention.